Alright, so we're given just an arbitrary square complex matrix, and it has some SVD, and we want to find an eigenvalue decomposition of the Hermitian matrix H, which is given by this. And first of all, note that H is in fact Hermitian because H star is, let's see here, you take 0, A star, 0, and you take the complex conjugate, or the conjugate transpose. And so when you transpose it, you get 0, and you get A star. No, when you take the, this ends up being A star star, A star 0. Because when you take the transpose, you end up bringing the A star to the bottom left and taking the transpose of that, and you end up taking the A to the top right corner and take the transpose of that, and then you take the complex conjugate of everything, which will turn those transposes into stars. So you have A star star on the bottom left and A star on the top right, and this is A star, and this is exactly H. And so H is indeed Hermitian. Okay, so we have this matrix A, and so it has singular values sigma 1 through sigma m. Here I'll assume that some of these singular values can be 0, that's fine. Okay, so we also know that A times Vi is sigma I ui for every single I between 1 and m, where Vi is the ith column of V and Ui is the ith column of U. That's just from our construction of this singular value decomposition. Okay, well then A star is, if you take the star of U sigma V star, you flip the order and you put stars on everything. So you have V star star, which is just V, then you have sigma star, and you have U star. But sigma star is real, or sigma is real, so sigma star is just sigma. So A star is V times sigma times U star. And so what that means, so this is the singular value decomposition of A star. And so sigma 1 through sigma m are the singular values of A star as well. And the equation AVI equals sigma IUI, if you rewrite that in terms of A star, it's A star UI equals sigma IVI. And those equations we're going to use to construct, eigenvectors of H. Okay, so let alpha be 1 over the square root of 2, and let Qi be, here, I wrote this like this just so that it'd be easier to write like in a line. But really what this is Qi is alpha Vi, and then alpha Ui, and then Qi plus m is negative alpha Vi and alpha Ui. So the vectors Q will look like, you'll have alpha V1, alpha U1, then alpha V2, alpha U2, all the way up to alpha VM, alpha UM. And then the next vector will be QM plus 1, which is negative alpha V1, alpha U1, and then negative alpha V2, alpha U2, all the way up to negative alpha VM, alpha UM. And of course, each of these QIs is a vector of length C, a vector in C2M. So the first M vectors are given by alpha Vi, and the second M vectors are given by alpha Ui. Okay, so then for each I, we can evaluate this thing, and this is written a little weird, and that's because I didn't realize until I was like writing out this problem that I needed to include this scalar alpha in here in order to make these vectors orthonormal. And so HQI is just this times this, because this vector is QI, and we can pull the alpha outside, and then we just have, when we do the multiplication, we have A star UI and A star in A times VI, and then we use these two equations that we have from before, and we have alpha times sigma IVI and then sigma IUI I. And then we factor out the sigma I out front, and we bring the alpha inside, and what we have on the inside becomes Qi. And so we have sigma I Qi. So HQi is sigma I Qi. So, and Qi is obviously going to be non-zero because each Ui and V, because each Vi and Ui must be non-zero because these are because U and V are unitary matrices, so none of their columns can be zero. So Qi is therefore going to be a non-zero vector, and so it's in fact an eigenvector of H with corresponding eigenvalue sigma I. Okay, what if we want to consider Qm plus 1 through Q2m? Well, if we take H and multiply by Qi plus 1, then this is the same calculation as before, but we have a negative sign up here. And then, let's see, our negative alpha Vi is going to be... what am I doing here? This doesn't look right. Alpha Ui. So this minus should be here, and this should be a plus. This minus should be here. And this should be plus. I don't know why I did that, because that doesn't make any sense. But anyways, you have these minus signs up here now. And then, oh wait. Okay, let me make sure that... No, I was right, because it flips the order. It flips the order. So when you multiply these two matrices out, the first entry up here, you're going to have 0 times negative alpha Vi times A star times alpha Ui, and that gives you this alpha star Ui up top. And then the this lower row here will give you the minus sign. And so you have negative alpha times AVI, and you bring the alpha out front. And then these things you can replace with the sigma i's, and then you can bring a sigma I and a negative 1 out front, and you end up with negative alpha Vi and alpha Ui inside this vector, and that gives you Qi plus m. And again, each of these Qi plus m's is non-zero for the same reason that each of the Qi's is non-zero. So therefore, Qi plus m is going to be an eigenvector of H with corresponding eigenvalue negative sigma I. So for each I, we know that sigma I is an eigenvalue of H with corresponding eigenvector Qi, and negative sigma I is also an eigenvalue of H with corresponding eigenvector Qi plus m. Okay, so now that we have the eigenvectors, we can sort of construct the matrix that we use in our eigenvalue decomposition. But if we, so this matrix is going to be Q, which is a 2m by 2m matrix given by just putting all of these vectors together. All of these Qi's are column vectors. Now we got to confirm that this is actually an orthonormal, that these columns form an orthonormal set, because we want Q to be orthogonal. Well, we don't need Q to be orthogonal, we just need it to be invertible. But, well wait, no, not orthogonal. We don't want Q to be orthogonal, we want Q to be unitary. We're going to prove that Q is unitary by proving that its columns are orthonormal. And then when Q is unitary, it's certainly invertible, and so that's what we'll need to use, really, is the invertibility, but it's actually just as easy to prove that it's orthonormal. So anyways, if you choose any I and j between 1 and m, and assume that I and j are not equal, and you choose a and b to be between 0 and 1, so basically what I'm doing here is I'm computing what would happen if you take the inner product of two separate columns of capital Q. And here we're assuming these columns are such that you're not taking the inner product of a column with itself, and you're not taking the inner product of the column qi with qi plus m. So those two scenarios are not covered by this equation. But every other scenario is covered by this equation by choosing some values of I and j and choosing some values of a and b. So anyways, what happens is the negative ones here don't matter, and all that matters is that when you do this inner product, you get this negative 1 to an exponent, then you get alpha squared, and then you get vi star vj, which, because of the v is in a unitary matrix, so its columns are orthonormal. Its columns form an orthonormal set, so the inner product of any two different columns is 0. And so this whole part is 0 since vi star vj is 0. And similarly, this part is 0 since ui star uj is 0. And so this inner product of these two vectors is 0. Then if we actually specifically consider the case of two different columns of q of the form, you compare qi with qi plus m, you take their inner product, and you get this. You get the minus sign, which comes from the qi plus m. You get the alpha squared, and again you have this vi star vi and the ui star ui. But because the columns of v are orthonormal, vi star vi is 1. So we get a negative alpha squared. And because U is also a unitary matrix, so its columns are orthonormal, so ui star ui is also 1. And so we end up with negative alpha squared plus alpha squared, which equals 0. And finally, and this is the part where I needed to introduce alpha. So if you take the inner product of any vector of any qi with itself, it can be of this form where I is between 1 and m, and then alpha will be either 0 or 1. If alpha is 0, then we're considering the case of when you're looking at q1 through qm, and if alpha is 1, we're looking at qm plus 1 through q2m. But anyways, you take this inner product, and you get negative 1 to the 2 alpha, you get alpha squared, get vi star vi, then you get alpha squared. Oh, there should be alphas here. Get alpha squared, ui star ui. So this minus 1 to the 2 alpha, well, 2 times a, no, it's not 2 alpha. It's negative 1 to the 2a, and 2a will always be even, so this will always be negative 1 to a positive power, so this will always be positive 1. We'll have alpha squared, and v star times v1 is 1, and then we get plus alpha squared times 1. So we get alpha squared times alpha squared, so we have 2 alpha squared. And remember, I chose alpha to be 1 over the square root of 2, and I chose it specifically for this equation, because now when you square alpha, you get 1/2, and when you multiply it by 2, you get 1. And so that's what you need in order for the columns of q to be orthonormal. If we didn't have this alpha here, the columns would be orthogonal, but not orthonormal. And them being orthogonal might be enough, but if they're orthonormal, then q is unitary. So thus q is unitary, and in particular, q is invertible. Because for q to be unitary, it means that it's invertible and q inverse is equal to q star. So that's just a special case of an invertible matrix. Okay, so the important thing here about q, beyond it being invertible, is the fact that its columns are the eigenvectors of h corresponding to the eigenvalues sigma 1 through sigma m, then negative sigma 1 through negative sigma m, respectively, in that order. So we define capital lambda to be a diagonal matrix consisting of these values. Then we have h equals q lambda q inverse is the eigenvalue decomposition of h. And we know this because from linear algebra, we know that if you want to find the eigenvalue decomposition of h, you let lambda be the diagonal matrix consisting of the eigenvalues, and you let q be a matrix of eigenvectors, where the ith column of q needs to be an eigenvector corresponding to the ith diagonal entry of the matrix of eigenvalues. And that's just a linear algebra fact. If that's not something you've covered, you can go through and prove that. There should be proofs in linear algebra textbooks, or you should be able to prove it yourself. But anyways, so we wanted to find an eigenvalue decomposition of H, and we found one, and so we're done.